Rohit Kumar Singh, the teaching assistant for this course, Statistical Mechanics. And this is the 12th live session, so this will be officially the last one. But we will have an extra session. You will get the mail maybe this week, maybe next week on Monday or someday. You will get the mail for an extra session. So that will be a 1 hour session, and there you can ask any any doubt or any question that you have regarding the course. So yeah, so but this is the officially the last week for the course. So last week I discussed the Bose-Einstein condensation, and I briefly derived the formula for critical temperature, and but I could not solve more. More problems. I think I did only one problem based on Bose-Einstein condensation. So I will solve some more problems, and maybe I'll again discuss briefly recap what is the Bose-Einstein condensation, and uh, then we can go to the problems. So before we start, anyone has any question or doubt? If no, then okay. Let's. So last week, I discussed the Bose-Einstein condensation. So, uh, so we know that for an ideal Bose gas, the mean occupancy of single particle states is given by this formula. So this one this formula everyone should know, right? Where Z is the fugacity. Everyone know this formula, right? This is the mean occupancy of single particle states for an ideal Bose gas. And now what we do is, instead of taking this single particle state as discrete, okay, uh, we take them as a continuous spectrum, and we define something called density of states. So density of states, okay, and so total number of particles, earlier it should be sum of these mean occupancy over all the single particle states. Now this becomes an integral, right? Because we are taking a continuous spectrum. So, and the integral, we can write them as okay, from 0 to infinity. And we also know the density of states uh, for an ideal Bose gas is given by this formula. So if anyone don't know this formula, I can derive it very quickly. I'm assuming everyone know how we get this density of states formula. Everyone is fine with it, right? Okay, so with this density of states, total number of particles is given by this. So we will take the constant terms outside the integral, and we divide the volume term here on, we take the volume term on the left side, and we have this integral. Yeah, sorry. Okay, and so this, when we calculated it, so basically we did the, we just evaluate the integral. uh, what we get is, so it is written in terms of the Einstein function, Bose-Einstein function g. But this is not that important. What is important is, when we take the limit tends to 0, temperature 0, uh, we get, so this lambda 3 is the thermal wavelength, you guys know. It is given by this formula, 2 pi m kt. Okay, so what you get is, here the subscript E is for the excited states. Okay, so we are not considering the ground state. Ground state is E equal to 0, because in this integral if you put E equal to 0, you get a 0, right? So this integral does not account for the ground state. Okay, so for the ground state, we have to, make an exception. I mean, uh, this whole calculation does not account for ground state. So for now, just think that ground state is, I mean, we don't know what is the number of particles in ground state. Okay, everything here is for excited state, so whose energy is greater than 0. Okay, and so this integral gives you this value. So this is the number of particles in excited state, okay, of an ideal Bose gas. And then we argue that since this function is bounded, okay, because z can have value from 0 to 1, right? So this function has also an upper limit. Okay, and its upper limit is given by, so its upper limit is given in terms of Riemann zeta function 3 by 2, which is almost equal to 2.612. Okay, so this number of particles in excited state should be lower than this upper limit. So this constant term and the upper limit of this Bose-Einstein function, which is zeta function of 3 by 2. Okay, so this number of particles in excited state is also bounded, and then we say that if you want to put more particles in the system, then you have to go to the ground state. Okay, because we still have not considered the ground state. We are assuming only the excited state here. So if your number of particles increases this Ne value, then they will be pushed to the ground state, which is the E equal to 0 state. Okay, if your n number of particles is greater than Ne, then this E ground state will be occupied. So what will be the occupation number, what will be the number of particles in ground state? So that will be just total number of particles minus the number of particles in excited states, right? And this has no limit. Okay, so this is unlimited. So if once you cross this threshold, all of the particles will go to the ground state, which has unlimited occupancy. Okay, and this is what we call the Bose-Einstein condensation, basically. And this happens, so this the condition of Bose-Einstein condensation is that your total number of particles should be greater than Ne, which is so Ne is equal to this value. So I'm taking the temperature term out, because that is the most interesting part, that this Bose-Einstein condition has a temperature dependence. Okay, so so if you fix the number of particles and volume at some constant value, then and vary temperature only, then also you can reach the Bose-Einstein condition, given your critical temperature should be equal to. So just take everything to the left hand side in this equation. This should be cube, right? No, it's fine. Yeah, because temperature has 3 by 2, so h cube over 2 by 3 is h square. And here is 2 by 3 dependence. Okay, so in this equation just we have inverted it in terms of temperature. So this is the critical temperature that you need for Bose-Einstein condensation. Okay, so this is what we discussed last time. Anyone has any doubt here? Please let me know. So this is the critical temperature for Bose-Einstein condensation. Okay, if everyone is fine with this, we can go and solve some problems based on Bose-Einstein condensation. Okay, so let's go to the first problem. Okay, so here there is a ideal Bose gas in a harmonic trap, and the question is which of the following are true. Okay, so there are these options. Now what does it mean, ideal Bose gas in a harmonic trap? So this basically means that this ideal Bose gas, its energy states have, its energy states are given by this harmonic, energy of a harmonic oscillator, right? Which is this energy. But we don't have to, use this formula for to answer this. So let's see. Uh, so the options are: in two dimension, Beck is only possible at zero temperature. Then in two dimension there is no Bose-Einstein condensation. Okay. In one dimension, Bose-Einstein condensation is only possible at zero temperature, and in one dimensional there is no Bose-Einstein condensation in thermodynamic limit. Now, which of the following is true? Anyone has any idea? How do you solve this problem? Anyone? So, okay, so let me try. Okay, so Bose-Einstein condensation, for this, uh, we need to look at the, so basically, what happens if we change the dimension? So far, what we have calculated here, so this condition, it is for three-dimensional, volume. What happen if we go to two-dimensional volume instead of three-dimensional? So what will change? So we have the number of, you know uh, number of particles given by this integral, right? Where this density of state is 2 pi v by h cube, this, okay. And this is for a three-dimensional volume. Now what happens when you go to two dimension or one dimension? So let us derive the density of state for different dimension. So basically we need this uh, energy dependence. Okay, how does density of state depends on energy? Then we can check whether this integral holds, like whether this integral converges or diverges. Okay, so here if you put here, so for 3D, this integral, so is basically, if you only consider the term that we are interested in, the energy terms, so it has e to the power half in the numerator, and in denominator you have e to the power beta e minus 1, let's say. We can take this outside. Yeah, Susanta has raised his hand. Have you any question? Do you want to ask something? Susanta? Okay, it's not. And so to check if this integral converges or diverges, we can take the limit of energy going to zero. Okay, there only it can diverge, and at in this limit, the exponential term can be written as 1 plus, beta e. So finally you have in the integral and in below you will have the only the e term. Okay, and finally you will have this. And so in the limit e going to 0, this converges, right? So this converges. Is it fine? Will it converge or diverge? Minus. Yeah. Now what about the one dimensional and two dimensional cases? So in general, okay. So the density of states in general, it depends on the dimension. So you know that the term intensity of state. So this is the volume term for the momentum space, right? And P is equal to, so E is related to P by this formula. Okay, so that's why you have square root of E dependence in the density of states. And in general, if you are in a dimension D, then density of state is proportional to this. Okay, you can check for so suppose for one dimension, density of state will be e to the power minus half, right? Similarly for two dimension, density of state will be constant because 1 minus 1 is 0, so it will be just constant. So there will be no energy dependence. And for these two cases, this integral.
Hello?
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 Yeah.
Good evening, sir.
Yeah, good evening.
Sir, I have a doubt.
Yeah.
Uh, In three-dimension case, when e tends to 0, epsilon tends to 0, we have written 1 by epsilon to the power 1 by 2.
Yeah, yeah.
So as we have put the condition that epsilon tends to 0, and we have written epsilon to the power beta, e to the power beta epsilon is equal to 1 plus beta epsilon.
Sorry, is this fine?
So, sir, yes, sir, 1 by epsilon to the power 1 by 2, it should be infinite, no, sir. When you will put in epsilon tends to 0, or as we have already put the condition that epsilon tends to 0 and have written e to the power beta epsilon is equal to 1 plus beta epsilon. So
Yeah.
no need to put this limiting condition again, sir.
So no, no, we are checking at when epsilon tends to 0, okay? And when you evaluate this integral, what you will get? So you will get minus 1 by 2 epsilon half, right?
Yes, sir.
And so this converges if you put for epsilon equal to tending to 0, right?
Yes, sir. Thank you, sir.
Yeah. Sorry, I did not evaluated the integral. So, but these two, if you put here in the integral, what will happen? So for the two-dimensional case, you can see you will have only the 1 by e dependence, right? So there is nothing on the numerator, and so this will also diverge because this will give you just, I mean, if you calculate it, it will give you e, and at e, I mean, it does not diverge, but it gives you basically 0, right? So you don't have anything for ground state. Basically ground state will have no occupancy, right?
Yes, sir.
Yeah. And similarly for one dimensional, you can also check this will diverge. So for one dimension you will have uh, minus half above and 1 by e here. So this is for two dimension. For one dimension you will have e to the power basically 1 by 2, right? And wait. Yeah, this for one dimension it does not diverge, right? So in one dimension, yeah, so there is a possibility of Bose-Einstein condensation. Oh, sorry, right? And in this option there is no mention of three dimensions. So yeah. Mm, sorry, sorry. No, no, no. This way you cannot. Uh, so for two dimension, we have just 1 over e, right? And this basically diverges. If you put e equal to 0, this will diverge. I miscalculated the integral, right? This will give you 1 over e square, which diverges. So only one dimensional bake is possible. Two dimension is not possible. Okay. So I think, yeah, this is the correct option. Mm. Oh, wait. What I'm doing? No. Sorry, I again miscalculated the integral here. That's what I was thinking. So this will be 1 over epsilon half, right? And this also diverges, correct? Uh, no, sorry, 3 by 2, yeah. If you calculate it, what you will get? Minus 3 by 2 epsilon minus 3 by 2 plus 1, which is equal to epsilon. So forget the constant here, minus half. So you get basically 1 over, yeah. So this again diverges, right, at equal to 0. So only the 3-dimensional case converges, other two diverges, correct? Everyone is okay with this? Guys, let me know if you have any doubt. Okay. Yeah, so I think there is no bake. So both options are correct. So in 2 dimension there is no bake, in 1 dimension there is no bake. So that's why only 3-dimensional gases can have Bose-Einstein condensation. You cannot get 2D Bose-Einstein condensation or even 1D. So this is very interesting. So to think about. Okay, if this is fine, let's go to the next problem. Okay, so this one is easy. So when we experimentally measure the critical temperature as a function of number density, we obtain a straight line with a slope of 3 by 7 in the log-log plot. That is, critical temperature is proportional to number density to the power 3 by 7. Now, the value of sigma, assuming that the phase transition observed in an ideal Bose condensation is. Okay, I think, okay, there is one information missing here in the problem. So it is given that the density of state is equal to a e a epsilon to the power sigma. Okay, so this is the information given, and we have to find what is the sigma here. Okay, And one information is given here is that the critical temperature is proportional to n to the power 3 by 7. So earlier when we had the square root dependence, we got the critical temperature proportional to what? It was 2 by 3, right? So you see, the critical temperature dependence on number density depends on how your density of state is dependent on the energy of the states, right? So to solve this, you will have to again, do this integral of, so you will have to again do this integral, putting this density of states here, okay? And but is there any simple way? Okay, so so let's go through the derivation, then we'll understand how this 2 by 3 comes about, and then we can generalize it for any number, any sigma. Okay, so uh, yeah, so this e to the power 1 by 2 dependence here in this integral, uh, this won't affect this lambda cube, right? This lambda cube will be there. No, wait. No, this will have effect on lambda cube. So temperature is basically coming from which term? So temperature is coming from this beta term here, right? So then yeah, then we'll have to see how, how if we do this integral with epsilon to the power sigma. So basically this integral becomes, right? Yeah. So we cannot directly do this integral. It will have to be done with using the Bose-Einstein function, the g function. But I have the general expression, so that I'll write, and I'll have to check how this general expression comes. So if you have energy density dependence on epsilon by sigma, then your critical temperature will have dependence on number density by 1 over sigma plus 1. So for now, just remember this, okay? So this is the general expression. I'll have to check the derivation. I don't know right now. So maybe this we can derive in the extra session. next week. But this is what the answer is basically. Okay, so if your density of state depends on energy with a sigma power, your critical temperature depends on number density with 1 over sigma plus 1. And now everything is simple because it is given that here the critical temperature is proportional to n to the power 3 by 7. So basically 1 over sigma plus 1 is equal to 3 by 7, and then your sigma will be equal to 4 by 3 simply. Right? So this integration we'll have to see how to do that with a general sigma dependence of energy states. Uh, yeah. So this maybe this I will try to discuss in the next session. This is an interesting one. But final answer is true. I mean, this is what you will get. You will get the n over 1, I mean 1 over sigma plus 1 dependence. Anyone know how this comes about? Has it been discussed in the lectures? I don't know. If anyone know, you can tell, or we can do it in the next session. It's okay if no one knows this. So someone has asked what will be the question pattern in the final exam. So I think final exam will have only there will be only objective, like multiple choice questions, right? I think there should be previous year's questions available, so you can check. I don't know if it is available or not. But the problems will be similar to what you get in the tutorial assignments. So just practice them and you'll be able to pass. Will it be computer based or pen paper? I don't know. I think it's computer based, right? I don't know about this. So you can ask the NPTL. I mean, you can mail the NPTL coordinators. But instructions should be, I mean, when you register for the exam, there should be instructions.
Sir, in the instruction, it has been mentioned that we will appear the pen and paper mode exams, right?
Okay.
So, will there be only numerical based question, or just like in our class, it has been taught how things are derived? When we
No,
spoke
no, no,
about
no, 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 no.
exam,
There will be only
only
no derivation will not be there for sure. Only numerical based question. Like you will have some maybe there will be fill in the blanks or only the multiple choice questions. We'll have to choose the options, numerical options. There will be no derivation. Don't worry. I mean, as far as I know, but you can check with NPTL portal. There should be some. I mean, the pattern of examination should be mentioned in the website. Okay, so let's do another problem. Okay, so yeah, this is now here the dispersion relation is given. So dispersion relation, as you know, is the relation between energy of the states and the k, which is the wave uh, wave constant. What do you call it? And so basically, you know that momentum is related to this wave vector as like this, right? Or and this is given, and also degeneracy factor is 1. Okay, so that means there is no degeneracy, and number density is given by is given as in square. Okay, now the question asks what is the single particle density of states. So we have to find the density of states, d or g, whatever you prefer. Okay, so how do you do this? How do you find density of states for a given dispersion relation? Anyone? So okay, so let me write the expression for density of states first. And we know that, so basically how we get the density of states. So first we know that the number of states is equal to volume in phase space divided by the volume of a single state, which is h cube. This is the h cube is the volume in phase space for a single state, right? And if you divide the volume in phase space by h cube, you get the total number of states that is available. Everyone knows this, right? This is a very general expression. And this volume in phase space, so you have, you have the integral over the position coordinates and then momentum coordinates, right? And and this this volume of the position coordinates, you can just take v, and this momentum coordinate volume in a spherical polar coordinate, you can write it as 4 pi p square dp. And if there is a degeneracy, then you multiply it by g, but since here there is no degeneracy, so you don't need it. Okay, now this you have. And but here the dispersion relation is given in terms of wave vector k, so we can transform this in terms of k. So as I mentioned here, so p is equal to h by 2 pi k, so dp will be equal to h by 2 pi dk, and you can substitute it here. So your number of states become 4 pi k square dk, and you have this 2 pi to the power cube in the denominator. Fine. And so this is the number of state in a you can say in a spherical cell of radius k and thickness dk. So we have integrated over the over the spatial coordinate, and this is the momentum coordinate. So you can say this is a spherical cell of radius k, and it has a thickness of dk. Okay, and this spherical cell has uh, volume 4 pi square uh, dk, and the number of states lying in this spherical cell is equal to this quantity here. Okay, so this is basically number of states in a spherical shell of radius k and thickness dk. Now what is the density of state? So density of state is simply number of state divided by volume, right? And so density of state will be and you can multiply the finite integral. Okay, yeah. Now we have to convert this k into E in terms of energy of the states, and that we can do here. So k will be E by A to the power 2 by 5. So dk will be A to the power minus 2 by 5 and E to the power minus 3 by 5 dE. So finally, density of states can be written as 1 by 2 pi cube 4 pi E by A to the power 4 by 5. So I have combined these two together. Sorry, I mean this and this here, but you are left with 2 by 5 e to the power minus 2 by 5 sorry, this should be 2, right? Yeah. Okay, 4, oh sorry, no, k square, so it should be 4 by 5. Fine. And if you evaluate it, so 4 pi over 2 pi by cube, let's take 2 by 5 on one side, then a will have so a will have minus 2 by 5, and from here you get minus 4 sorry, yeah, minus 4 by 5, so total it will be minus 6 by 5, and epsilon will have minus 3 by 5 and plus 4 by 5, so it will be just 1 by 5, right? Yeah, so you will get 1 by 5 over, and pi square get cancelled, 2 get 2 to the power cube get cancelled. You have 5 pi square a to the power 6 by 5 dE, and this is your density of state. Let's see if it matches. So it matches with this one. Yeah. Okay, so this is how you can calculate density of states for any dispersion relation given. You will have to just remember this formula here. This is the general formula for number of state. Is it okay? Anyone has any question on this? Hello? Okay. Okay, so yeah, that is all for today, and we will do this in the next session. This is important, and doing this we will also understand. I mean, how this Bose-Einstein condensation works for different uh, energy state dependence, right? So this is a very simplistic case where you have under square root of E dependence. You can have any dependence on the energy of the states. So how we get this relation, this temperature dependence on number density? I think it will be interesting to see. So that we can do it the next extra session. So if you have any doubt or any question, please ask. Oops, sorry. So this information we did not need it this in square in this problem. Is it fine for everyone? Okay. What is the exam pattern? Yeah, so that we discussed. So it will be mostly multiple choice questions. There will no derivation type problems. Just numerical. You'll have to solve some problems based on the concepts that you have studied. You will have to tick the options. That is all. So I'll suggest just go through the tutorial assignments that you have got for the 12 weeks, and try to practice that as much as possible, so that I think then it will be easy. The exam will not be much of a problem. Reference book. So again, like for this course, uh, I think the lectures are the best, and uh, I mean, Patharia is good, but there you won't find any, I mean, problem and solution. Like there are no example problems there. For concepts, Patharia is good. Reef is good. Uh, but yeah, I mean, I would suggest to practice the assignments as much as possible. So when is the exam? Like the date of the exam is, do you guys know? Hello?
May 4.
Yeah? May 4. Okay. So May 4. Okay, and then there is some time. So maybe in the next session yeah, I will try to give you some book reference. Okay, I don't have any particular book in my mind now, but I will find some books which can help you. So yeah, I'll tell the name of the book in the next session. For I mean basically for problems and solutions, so that uh, yeah, but there will be an extra session next week. 1 hour session there will be. Yeah. Okay, so then yeah, see you there. Uh, we'll have the last session maybe on Wednesday. We'll see. You will get the mail. Okay, so yeah, let's close the session for today and see you again. See you on Wednesday. Yeah. Bye. Thank you.